Our next topic of study is what is known as optics, which has to do with lenses and mirrors and light and all of those fun things. And for the majority of the time, we are going to be focusing on what is called the ray model. And the ray model ignores the fact that light is a wave and just thinks about light traveling in straight lines. And even though it is a wave, that isn't too important to a lot of different optical phenomena. We can explain how telescopes work and glasses and contact lenses and mirrors and all of these things just by thinking of light as traveling in a straight line and doing a bit of geometry. This is sometimes known as geometric optics because you just have to deal with angles and all sorts of things like that. Alright, so the ray model of light. You've probably thought about or been taught how we see things. It's because light bounces off objects and that light hits our eye. But if we think about that a little more deeply, light is hitting every single point on an object and it's bouncing off in all directions from every single point. That's why you can see an object no matter where you stand, as long as it's not being obscured by something else. So imagine this pencil sitting on the desk in front of you. Anybody in the room could walk around and see that pencil, and that's because light is heading out in all directions. But you're not seeing, it's not like there's one light wave that comes from here and one from here, and you're seeing all of those light waves as you move back and forth. Each point is emitting what we would call bundles of light, so to speak, in all directions, and just one little bundle of light hits your eye. And that little bundle of light left this one little point here. At this little point here, there's also light emanating out in all directions, and another bundle will happen to hit your eye that wasn't actually in the same initial direction as this one because it had to leave at a different point. So in order to put the picture together of this pencil, you actually have several bundles of light from every little point on that pencil that are going into your eye. The other important thing that I want to point out here is that these light rays that you are able to make out as a certain portion of the pencil, they have to be diverging. They have to be spreading out. That's how our eye is able to make images. We'll see later there can be instances where light rays are converging. And in that case, if you had converging rays, even if it wasn't like at the point of convergence, if your eyeball was right here and you had these converging rays going into it, you wouldn't be able to make an image. You might be able to perceive some light hitting your eye, but it would be blurry at best. You wouldn't be able to make a nice sharp image. The only way that our eyes are capable of making sharp images is when we have a series of diverging rays entering our eye and being focused back on our retina. Okay, so keep this in mind. This is how we see things. This is what's required to be able to make a sharp image of an object. And we can fake this. If we have a projector, the object isn't actually there. But if the projector or something like that can get diverging rays to hit our eyes will think that there is an object there. Alright, one of the more important principles for all of this optics stuff is if you have a reflecting surface, you can typically think of this as a mirror. We have the law of reflection, which simply states that the incoming ray will leave at the same angle that it came in. I think we mentioned this briefly when we looked at waves. Typically we measure the angle with respect to the normal or the perpendicular line to the surface. So here is our angle of incidence, or the incoming angle. Here's our angle of reflection, or the outgoing angle. So if we have a little bit steeper here, then it will go, I don't know if that's any steeper or not. Anyway, moving right along, this is kind of an important principle for reflection. Now, normally we don't have perfectly smooth surfaces. So if we think about the light that hits, take the desk in front of you again, if you have a desk in front of you, if not, imagine one. Say the light is all coming in from the same direction. And this happens if the light source is far away. So if there's a desk lamp, this probably is not going to be the case. But if your light is illuminated, if your desk is illuminated from some light on the other side of the room, then this will be closer to true. And if something's illuminated by the sun, that's a very distant light source, and so all of these rays will be nearly perfectly parallel coming from the sun. Now, the surface of your desk, even though it might feel smooth, is not actually smooth on the microscopic level. It's going to be jagged like this. And so for each ray coming in, each individual ray obeys the law of reflection. It's just that the different angles in the material mean that they get reflected out at different angles. They get scattered, we call this. And so this is diffuse reflection. Now, this is good and bad. I mean, if you want all the light to go to one place, this isn't going to work so good, but this helps you see the desk from a variety of angles, as I mentioned with that pencil, because this light is going to be scattered out all over the place. If all the light just bounced off and went to one single location, you would only be able to see that desk if you were standing in one single location. So it's an idea like this. Rather than having the light go out where you can see it from different areas, you wouldn't be able to see the desk at all right here. It would be invisible to you, or black, I guess. You would only be able to see it if it bounced right here. So another way to think about this, imagine if you have like a laser pointer and you shine it on a desk. Now, anybody who can see the desk is going to be able to see a red spot on that desk, because that laser pointer light is going to be scattered diffusely throughout the room. Whereas if you shine it on a mirror, most of that light is going to bounce straight off, and you might see it on a wall where there's a nice bright red dot. Now, you could probably see a little bit of a red dot on the mirror because it's not a perfect reflector. If you had a perfect reflector, you couldn't see a single thing on the mirror. All you would see is the dot on the wall where all the light got reflected to. But because the mirror has some jaggedness to the surface, you can see kind of a dim red dot on the mirror and a bright red dot on the wall. Here it's kind of opposite. If you have a smooth desk, you might still see a dim red dot on the wall, but you'll see a bright red dot on the desk where the light, most of the light is getting bounced out at different angles. Alright, let's look at mirrors a little more closely. So if I'm looking at an object, as I mentioned earlier with that pencil, light is coming from all points of the object, but let's just focus on a point on the top of this bottle thingy here and a point on the bottom, otherwise our drawing gets a little too crazy. So as I mentioned, light is going out in all directions, so if we pick out these two rays, and the reason why we pick these two is these are the two that are going to make it into our pupil. There are other rays heading out in all directions here. We're just ignoring the other ones, right? So this ray goes and bounces and hits the top of our eye. That ray goes and bounces and hits the bottom of our eye, and so we're able to perceive that point. This one here bounces there, and so forth. And you can see just by the symmetry of this picture what you're going to see. Our eyes, when they see divergent rays, we're able to make an image out of that. Even though we aren't looking at the rays coming directly from the object, these are coming from the mirror. Our brain is able to make an image out of that, but our brain usually thinks that light travels in straight lines. That's how we interpret the light hitting our eyes. So our brain says, oh, there must be an object over here from which these lines, these light rays traveled in nice straight lines to our eyes. So that's why we see this image in the mirror. It's not actually coming from this location. This is behind the mirror, right? You look behind the mirror, if you don't have one mounted on the wall, there's nothing there. You wouldn't be able to see anything there. But you look in the mirror, and it's kind of this trick of the mind, I guess, and we perceive something as actually inside the mirror. Back to my idea of symmetry. Sorry, I got distracted. The symmetry of this situation shows that you will see the object just as far in the mirror as the actual object was from the face of the mirror. So what I'm saying here, this DO, that is what we usually call the object distance. It's the distance from the object and the mirror. And DI is the image distance. So this is image and object. So whenever you have a plane mirror, and by plane we mean planar or flat, then the object distance equals the image distance. DO equals DI for all plane mirrors. The other thing we can see from the symmetry of this little diagram here is that the height of the object is equal to the height of the image. Everything is perfectly symmetric, so everything's going to be the same size. So we can also say that the object height, HO, equals the image height, HI. So they will be exactly the same size and exactly the same distance from the mirror. Well, this distance, actual distance from the mirror, and this perceived distance from the mirror. Some other interesting things about mirrors. Here's a little situation. If you think about how large a mirror you need to be able to see your entire self from the tip of your head to the bottom of your feet. If I'd asked you that before showing you this image, you might have said you need a length that's equal to your height. A length of mirror that's equal to your height. Turns out that you need a length of mirror that's equal to only half of your height. And here's how that works. So if you think about a light ray, and here we're going to kind of start ignoring the bundle thing, because the bundle that hits our eye is going to be pretty small. So we just imagine a ray of light. This kind of represents the bundle of diverging rays that are going to hit our eyes. From the top of our head, it's going to bounce off the mirror, and then it's going to hit our eye. It doesn't have to, we don't have to have the mirror all the way up here at the same height as the top of our head, because the law of reflection says this is going to hit at the midpoint between our eyes. So here's like the level of our eyes, there's the level of the top of our head. Law of reflection says we only need a mirror that goes up to the midpoint of that incoming ray. Okay, and we can have the same argument for your feet. So a ray comes from your toe, bounces off the mirror, and goes to your eye. So this here is the midpoint of the distance between your toes and your eye. So you take the distance from your eye to your toes and cut it in half. Take the distance from the top of your head to your eyes and cut it in half, and that leaves you only with half of the distance, or half of your entire height. So I didn't mention this distance from A to D at all, and what's interesting is that this argument doesn't depend on your distance from the mirror. So let's take a look at what I mean by that. If instead of having the mirror where it's shown in the picture, say the mirror is back here somewhere. Oh, didn't draw the line that I wanted to draw. Let me try that again. Okay, there we go. So let's say that this is our mirror back here. I can have the exact same argument. So I could have a ray coming from my foot. Goodness. Trying to get some straight lines here and it's not cooperating very well. Alright, a ray coming from my foot meets the bottom of the mirror, and then a ray bounces off the bottom of the mirror and goes into your eye, and one comes from the top of your head, hits this farther mirror, and one more here from the top of the mirror back into your eye. Okay, so we can have the identical argument that the mirror just needs to be half of your height to have this bounce off and into your eye, and that bounce off and into your eye, because this bouncing point is still going to be the midpoint. And so what that means is your distance from a mirror doesn't affect how much space you take up in the mirror. And I know all of you guys are going to be like, yes it does, yes it does. Well, that's kind of an optical illusion, because what happens when you move toward a mirror and away from it, the other objects that aren't the same distance from you appear to change size, and that makes you feel like you are actually changing size, because your size is changing relative to those other objects. But if you actually stand in front of a mirror, if you've got a marker or something that's not going to be permanent on the mirror, put a mark at the top of your head and on your waist or at your chin, whatever, and then back up or scoot closer and align those marks with the top of your head again. You will see that you actually take up the exact same space in the mirror, whether you're close or whether you are far. Here I'm going to try yet again to put a link to another video talking a little bit more about some mirror stuff, and hopefully it'll work this time. Alright, talk to you later.